Hello everyone, welcome to the presentation of SSD thermal impact study with different workload by myself Mohanraj Veerasamy and Ganesh Babu Vasudevan from Samsung Semiconductor in the R&D Center and Javier from Samsung Semiconductor Denmark. And this paper will be covered by myself and my colleague Ganesh Babu Vasudevan. Solid state storage devices has come a long way. From being a cache device for hard disk based applications, flash based SSDs have established themselves as a high performance alternative to HDDs. The benefits of SSD are well known. That includes mainly system boot time is 1/3 of HDD, less power drawn, reduced noise, and greater mean time between failure. As a main storage device, SSD should have capability to store more data. So size of SSDs keep getting scaled up. Also, SSD has to be more reliable and should be able to perform consistently for a longer duration. To meet these performance and reliability requirements, SSDs are keep evolving over the time with help of advancement in technology. But at the same time, SSD form factor remains same or even getting smaller. During initial development, most of the SSDs were developed with 2.5-inch form factor. Then there is an introduction of S.M.A.R.T devices which are used mainly in client applications like laptop. In recent time, M.2 SSDs have become increasingly popular due to its small form factor. However, its small form factor, high capacity and high performance would also result in significantly higher power density. As the power consumed by SSD is increasing and there is a less space for heat dissipation, it results in more heat getting generated in SSD. Most of SSDs are rated to operate within temperature range of 0 degrees Celsius up to max temperature of 70 degrees Celsius. This range is about same for every consumer SSD currently available in market, but it can slightly change based on the model and form factor of SSD. Even though technically SSDs can operate at 70 degrees Celsius, for safety and reliability purpose, mostly operating temperature of SSD is recommended to be between 30 degrees Celsius and 50 degrees Celsius. If the temperature increases, then there is a chance of more bit errors occurring and existing recovery logic could not able to correct it. So the temperature is one of the main factor in flash SSD data reliability. The overheating of SSD could also possibly lead to electronic component damages and overall system failures. Hence, thermal throttling plays important role in operation of SSD. The thermal throttling is a process of cooling down temperature of SSD by reducing the overall performance. Based on the need and requirement, different methods have been used by different OEMs. The thermal throttling algorithm maintains an operating temperature threshold. Once this threshold is reached, the algorithm forces drives performance to reduce to use less energy and subsequently self-cool. And once SSD's temperature drops below a lower threshold value, then the thermal throttling algorithm releases the performance throttling and allows drive operation to increase back to regular operating condition. From this, it is evident that once we enter into thermal throttling mode, the performance of SSD is hardly hit. The consistent performance can be a paramount important in data logging applications. Therefore, it is important to reduce frequency of device entering into thermal throttling mode, and also once it enters into the thermal throttling mode, it should be able to come out quickly. This requires better understanding of different workloads and its impact on SSD temperature. The SSD temperature increase varies based on the workload. For example, based on the different type of I/O and manner in which data is written to SSD and chunk size. To cover further about this study, I would like to call upon Ganesh.
Hello everyone, and thank you Mohan for the intro. We have seen the introduction of this SSD thermal study, and then now we are going to start with impact study on client product. So the client SSDs are growing in popularity for consumer data storage as an alternative to HDDs. A quality SSD must offer low power consumption, high power density with excellent thermal management, and also overall energy efficiency. In addition, growing consumer products demands improved speed and performance at lower cost, but also in smaller size. So we will see the workload item which impacts the temperature. Chunk size. Chunk size in I/O is very crucial in determining the temperature. Smaller chunk I/Os are more common in client devices. In small chunk write, NAND pages are either used up fast as data is either deleted or rewritten. These pages are marked for garbage collection process, and also it places heavy load on I/O as well as garbage collection process, which severely impacts the performance. This is more evident in case of random I/O compared to the sequential workload. The best case scenario is always writing as close to the page size as possible. There are ways of easing the pain of smaller size data transfer. Some SSD devices use external DRAM cache to accumulate sectors until a page or more worth of data is available to commit to the flash. Actually, this is a double-edged sword. In case of any power failure, the cache data is completely lost. So to overcome this can be supported by a properly designed power failure cleanup by either having an support system at drive level or better at the system level, or like both combinedly. This also involves multiple component at SSD to work for small chunk size I/O rigorously when compared to the large chunk size I/O. And when we come to this study also reveals that random workload temperature increment is less for higher chunk size I/O when compared to the lower chunk size I/O. As you can see from the graph, for the random write and read, the higher chunk size I/O having the lower temperature, whereas the lower chunk size I/O is having higher temperature, irrespective of the density. So the next item which we are going to see is temperature saturation. Generally, the general understanding is temperature keeps rising for continuous I/O. But in real case, temperature saturates after reaching a steady state point. It behaves in same way for different chunk sizes and also for sequential as well as random. So from the attached graph, it is clear that in case of both sequential as well as random and across all the chunk size, the temperature saturates at a point and it stays steady. So the same observation is seen for read also in case of both sequential as well as random and across all the chunk sizes. So the next item we are going to see is read and write. So in case of read and write also, the general understanding is write generates more power, and due to which the temperature rise in write is more when compared to the read. But the temperature saturation point of read is slightly higher when compared to the write. It remains same for all the chunk size and for the random write as well as read. So here we can see that for sequential also, in case of write and read is having higher temperature when compared to write. And earlier we have seen for random workload. So the next item we are going to see is operating temperature. Basically, we are trying to compare the operating temperature between the currently used SSDs with the previous era SSD. As per study from the Usenix paper, operating temperature of previous era SSD is much higher when compared to the currently used SSDs. So the previous era SSDs temperature range from 100 to 170 Fahrenheit. But the operating temperature of recent SSDs are much lower and in the range of 90 to 100 Fahrenheit. This could be due to improvement in thermal characterization of the components used in the recent SSDs. So the Usenix paper also attached in the document for the reference. And the next item is form factor and core. As discussed earlier, there is reduction in size of SSD and also demand for higher performance. This requires more core getting added to the SSD for better I/O and garbage collection management. Since more number of core is getting added, this results in more power consumption and in turn generates more heat. As you can see from the attached graph, for M.2 3-core sequential write, the steady state temperature for each chunk size is varying between each other, whereas in 2.5-inch 2-core sequential write, the steady state temperature remains same for all the chunk sizes. And this is for sequential workload, and the same is seen in random workload also. So in random write for M.2 3-core product, the steady state temperature for different chunk size is different, whereas in 2.5-inch 2-core product it remains same. So the next item which we are going to discuss is number of component. So the SSDs are made up of hundreds of passive component as well as NAND, DRAM, specialized integrated circuit, and at least one controller. A study from the Computer Architecture and Memory System Labs at the University of Texas, Dallas, presented at Hard Storage 2014, reported that there were 64 times as many chips and channels in current SSD when compared to 12 years before. So from the attached graph, it is very clear that the 2 TB steady state temperature is higher when compared to the 250 GB due to the number of components. So this is for the random workload. And it remains same for the sequential workload also, where for the 2 TB, the temperature rise is higher when compared to the 250 GB product. The next item which we are going to see is frequency. So irrespective of the interface speed, the temperature pattern is remaining same. So here we can see the data is for the sequential write with 1.5 Gbps and 6 Gbps, and the temperature is remaining same for both 2 TB device as well as 250 GB device. Till now we have seen the workload impact on client. Henceforth we will be seeing the impact study on DC. The DC product mainly differs with the client product in terms of power and determinism of I/O. There is no power limitation for DC as compared to client, as they are connected to server which is connected to the main supply. So the only point we have here is DC products will not have automatic power management. So this could be the reason for not seeing any ramp in temperature. So as you can see, like there are ramps in client and there is no ramp seen in DC with respect to the different chunk size and also with respect to the number of components and between the write and read. In the attached graph, it is very clearly visible that in case of random workload for write and read, there is no ramp seen. And then same is observed in case of sequential also for write and read across the different chunk size. Conclusion. Thermal throttling is an optimal way to continue constant drive operation to prolong its operational lifetime and to improve data integrity. Thermal throttling lowers the temperature but also limits the active resource due to overheating problem, and continuous power throttling hinders the SSD from integrating more resources. As form factor, performance requirement and cooling criteria evolve, SSD thermal management must also needs to be evolved to achieve optimum performance and stability. This study reveals few key points like increase in temperature for read workload is slightly higher than write. Increase in temperature is directly proportional to the number of components added to the device. Currently, there is no such study and not much details available on different types of workload impact on temperature. So this study will help in fine tuning the thermal throttling policy based on the different workloads. Thank you, Sneha, for this opportunity, and please share your feedback. Thank you.